book, which I want to provide you some extra information on, is being able to use what's called Bra-ket notation. And that is useful because it's just going to make writing these complex math equations so easy. So let's go through it. Okay. So this thing, what I'll call the left-hand side, is called a bra, and this right-hand side is called a ket. So oftentimes people say bracket notation, but it is technically Bra-ket. More famously, this is called Dirac notation for the scientist Dirac. I'm failing to think of his first name. But Dirac himself came up with this notation. We now more generally call this Bra-ket. Okay. So a ket is used specifically for wave functions, and a bra is used for the complex conjugate of that wave function. Okay? So for example, if I write psi of x, okay, and I want to let my audience know that psi of x represents a wave function, then I can put it in a ket like so, okay? And that tells everybody, at least everybody who's familiar with Dirac Bra-ket notation, that we're talking about a wave function. And now what I place in the ket is actually up to me and how I define my functions, perhaps when I'm writing a paper or spelling it out in a presentation. So I could just say psi x in the ket, and we know now that that's a wave function. I could even just put x in a ket, and that would tell me that's a wave function. Or if maybe I wanted to talk about the wave function of state I could even just say this, and that tells my audience, because it's a ket, it's a wave function. And of course, in my written text or in my oral description of this, I would tell my audience, we're talking about state I, and perhaps state I is a wave function. Or, well, I shouldn't say perhaps. Perhaps state I is a ground state. We would definitely know it's a wave function just by putting it in a ket. Okay. Another thing that we could do if we wanted to be really slick, suppose I was talking about the hydrogen 1s orbital, right? I could go H1s like that in a ket. And now most chemists would recognize this as the hydrogen 1s electron wave function. So I've kind of got some freedom of what I want to put in the ket, but the ket means wave function. Okay, so let's talk about the bra. So the bra is for the complex conjugate. So we wrote psi star x as the wave function of psi of x, okay? So I could put that psi star x in the bra, and that tells me that I'm talking about the complex conjugate. I could even just put, x like that if I wanted to. Oops. But really, I don't even have to put the star right there, because if I put this in a bra, that automatically means I'm talking about the complex conjugate. And in this same notation here, right, I could even just say state I, and that would tell me I've got a complex conjugate of state I, and maybe state I is a ground state. Or back to this other example, right? If I wanted to talk about the complex conjugate of the hydrogen 1s orbital, right? I could throw that sucker in a bra, hydrogen 1s, okay? And that tells me I'm dealing with the complex conjugate of the hydrogen 1s orbital. So now how do we apply this to make the math simpler? So for example, when we're talking about the square modulus, so we recognize the square modulus, in one notation, we just wrote this as psi x squared. That tells me it's a square modulus. I really know that the square modulus is technically the integral of psi star psi dx. However, in this Bra-ket notation, if I write a bra and a ket together, only separated by one line, this means this whole integral. Pretty sweet, okay? And so now let's suppose back to this example, right? Maybe I'm talking about state I. We'll go back, we'll use the state I notation. So if I was writing this, you know, if I just did this right here, just that simple notation. And now suppose that I'm not even dealing with a one-dimensional wave function. Suppose that this is a proper three-dimensional spherical coordinate system, okay? Just by writing I in a bra and a ket, this would actually imply the triple integral of psi I star psi I d tau. It would mean all of that. So this is definitely a very convenient shorthand notation, but we have to recognize what it means, okay? So there's a couple examples that I'm going to work through, and I would encourage you to work through these on your own first to see if you got it. Let me find my cheater notes here. Okay, so express the following in Bra-ket notation: orthogonality, a normalized wave function, an expectation value, and a basis set of three states I, J, and K. Let's do it. I'm going to go through my notes just to make sure. And if you want to pause to make sure that you're getting it right, try it on your own while I'm kind of flubbing through. Okay, great, I found it. Okay. So let's go for it. Okay, first one I'm going to do orthogonality. Okay, so let's do that right here. All right, so I'll remind you, orthogonality looks like the following. The integral of psi of state I, complex conjugate, psi j d tau equals 0, where I cannot equal j. So how would I express this in Bra-ket notation? Well, quite simply, I could just say I in a bra, j in a ket with a shared line does not equal to 0. And bam, look how easy that was to notate. Assuming that I know the Dirac Bra-ket notation, okay? So now what about a normalized wave function? Okay, let's do that over here. So I'll remind you, let's see here, normalization. Okay, if we write what a normalized wave function looks like, let me just make sure that I'm going to write this down correctly. Okay. Okay, great. So I'll remind you, if I have two normalized wave functions, okay, that's integral of psi I star psi I. So I can only normalize wave functions if they are in the same state, okay, d tau, and that equals 1. So this just tells me the wave functions are normalized, okay, right? We know that to find the normalization constant, I would put an n squared out there, okay? And that would allow me to find the normalization constant. But if I just want to tell my audience I have two normalized wave functions, then I can just simply write I equals 1. And just this simple notation tells me a wave function of state I is normalized. All I got to do. Brilliant. Okay. So how about expectation value? So now this is where this one is going to change a little bit. Okay. And so for expectation value, I'll remind you what the mathematical operation is. It is integral of psi I, complex conjugate, omega, right? We make the operator sandwich, psi I d tau equals lowercase omega. Okay? So now I have to change this up just a little bit to write this in Bra-ket notation. So here's how I do it. I write the complex conjugate in a bra. Okay? I make the operator sandwich like so. I put I in a ket, and that all equals lowercase omega. Okay? So that's how I could express the expectation value using this shorthand Dirac notation. Okay? And then finally, for my basis set, I'll pause for a moment while I'm flipping around for the answers. And you can try to do it on your own. Okay, beautiful. So if I wanted to now, so I'll write out what the mathematical operation of my wave function is. So I'll write psi equals, and so we've notated that that's 3 states. Okay, so there's going to be some constant for state I times psi of I plus some constant for state j times psi of j, and some constant for state k times psi of k. Okay? And so now, when I write this out in my Dirac notation, it's not really going to be shorter necessarily than how I just wrote it, but it's still going to be a good way I can apply writing this. So I will write that my wave function, so I just put psi in a ket, which is fine, okay? And so now I'm going to say that that's this constant, right? Ci times the wave function of I, okay? Plus this constant of state j times the wave function of j. And notice here now I'm just putting I in the ket because, again, since I've put it in the ket, it tells me it has to be a wave function. And then finally plus ck times some state k. All right? So as we progress through this class, our wave functions are going to get more complicated. All right? Our mathematical operations, this orthogonality, normalization, expectation values, and we will eventually use a basis set. We're going to have to use basis sets to describe the atomic orbitals. Those equations are going to become humongous, too cumbersome to write out. So this Dirac or Bra-ket notation, both names are okay, whichever you prefer. It's going to become extremely useful, you know, especially if you're writing up your exams or in your Mathematica files, for example, if you want to use this really slick notation to make a nicely formatted answer. But also, as I'm writing out of my lecture notes, it's going to be very practical for being able to write and use this shorthand. Okay?